Okay, hello and welcome to this episode. So what we're gonna do today? Well, today we are going to do mesh analysis, but this time we'll do it with AC circuits and capacitors and inductors, because as you remember, like last time we did it like a long time ago. It was like one of the first videos. We did it, but we did it with only resistors and only DC sources, and that is very different from using AC, and you'll see in a second why. And you'll see why if doing it into the AC method it's even worse than into the DC method in a second. But anyway, alright, so I'll just put this on here. First let's go through some basics, and one of those basics is basically conversion. Okay, so there's this special thing that you can do, which is converting components. More importantly, you can convert sources. For example, I can change this voltage source into a current source by simplifying the formula. I it's equal with E over Z, and because this side's 100, we'll just put 100 here, and at an angle of 0 degree in phase divided by 5 ohms, because when you calculate those two you'll get 5 ohms, an angle of 53.13 degrees. We divide those two polar forms, we get 20 amps at an angle of minus 53.13 degrees. And we think, well, what, they just replace the voltage source? And the answer is no. The way you convert it into a current one is to replace the components, like the total Z value, in parallel. Now the total Z value can be any Z value really. So the way you write it to be something like this. We'll put the current source here, the 10A at an angle of minus 53.33. Then you have the wire going through. You have point A, which is the top point here, because it was going in that direction, let's say it like that. Then you have it going under, and then you have the two components, the resistor and the inductor. And there you go. And then it meets back again at point A with the comma on the top. Alright, so basically that is the conversion. And the important thing that you need to remember, like it's a very simple formula to apply to, but the important thing that you need to remember is that the current source will be in parallel with the resistor and with the inductor. So don't do the mistake of forgetting this step. Don't do the mistake of just replacing here the voltage source. And you can do the same one for the current as well. As you can see here from the next example, we need to calculate the total Z. So Z will be equal with ZC times ZL all over ZC plus ZL. That's equal with XC at an angle of 90 degrees multiplied by minus 90 degrees multiplied by XL at an angle of 90 degrees. This one is the positive one. Okay, all of it divided by minus JXC plus JXL. That will be equal with 4 at an angle of minus 90 degrees multiplied by 6 at an angle of 90 degrees, and all of it divided by minus J4 plus J6, and that will be equal with 24 at an angle of 0 degrees, because minus 90 plus 90, that gives you 0, divided by 2 at an angle of 90 degrees. We did the division, that will give us 12, and the degree will go into the negative side, so that will be at an angle of minus 90 degrees, and it's our answer. And now we can calculate the current, because the voltage, because that will be simply be I multiplied by the value of Z that we just calculated. So that will be equal with it's 10 amps. Let me actually turn on the flash. Is it better? No, it doesn't make much of a difference actually. Okay, so this will be the 10 amps, so that'll be 10 at the angle of 60 degrees multiplied by 12 the angle of minus 90 degrees, and the answer that we'll get will be 120 at an angle of minus 30 degrees. Alright, and remember again, don't forget, you need to do transformation as well. You will have to replace it with the component, the 2 points A and A with the comma, with the voltage source, which will be this one here, the 120 at an angle of 30 degrees, and because the Z total is written as 12 at an angle of minus 19 ohms. Instead of putting those two components in series, we can just simply write it like this as a capacitor, because it's got minus 90 degrees and it's got an XC value of 12 ohms. Right, so that was pretty simple as well. And not only can apply it to voltage and current sources, we can apply with depending sources as well. And you may wonder, like, well, Alex, what's a dependent source? Well, we didn't really work with them that much actually at all for so far. From what I know and I read, a dependent source is basically a voltage or current source that is depending on other components. And you may say, well, yeah, that's like all the all the sources. And no, it's kind of not. For example, like this one, it's 120 volts at an angle of 30 degrees all the time. It never changes, even if I change this one with 24 ohms or with 50 ohms. But this one, which is like 20 volts and it's got a resistor of 5k ohms, well, if I change this one to 10k, then the source will change as well, because it's depending on the components around it or on a previous circuit or something like that, you know. Basically, it can change, it doesn't stay fixed. It's not like you plug it inside the socket and it's always the same value. It's more like it's part of a circuit and you just extract that value from that circuit. But anyway, let's keep going. Alright, and this one it's very simple as well, because we apply basically the same formula. It'd simply be I is equal with E over Z, and that's equal to 20 at an angle of 0 degrees divided by 5k at an angle of 0 degrees, and that will be equal with 4 times 10 to the minus 3 amps at an angle of 0 degrees. And we can rewrite this one, very importantly, as a depending current source. It won't be an independent one, it will be a depending one. It's 4 times 10 to the minus 3. There you go. And then we just write in parallel, so there will be the resistor, and this will be the rest of the circuit, which is basically open, really. Z 5k ohms, and there you go. Alright, let's go to the next one, because it's of course it's one more. I'll also show you how to convert it from a current depending current source, which is this one here, because it's got the rhomb instead of the circle, to a depending voltage source. So for this one, it's basically E is equal with I multiplied by Z, so that's equal with the 100 amps, so 100 at an angle of 0 degrees multiplied by 40k ohms at an angle of 0 degrees with the resistance here, and then that will be equal with 4 times 10 to the 6 volts. My god, that's a lot actually. Oh well, at an angle of 0 degrees, so we can just redraw it like this. We put the sign in here, so that would be 4 megavolts plus minus, and we connect it in series, leave the rest of it open. That would be 40k ohms. Alright, now this is simple as well. So yeah, this stuff is the easiest stuff that we'll do today, because don't worry, that's not the entire video. We are doing mesh analysis as well, but okay, so let me explain to you like something very important that I don't really want to do an entire video based on, but it's important to know for mesh analysis. There are things called matrices, and you should have learned about them if you are in the first year, like I did during your maths classes or lectures or whatever you want to call them. And what's a matrix? Well, basically it's a table like this one. There's got like 4, 8, 10 and 5. And what you can do with them, you can do one graph like that and divide by another one like that. That's got 2, 10, 6 and 7. You know, and you apply the formula to do it and you get a number. But you may say like, okay, so I can make this one into a number, but why would I do that? Well, we remember simultaneous equations. Let's say V1 is equal with 2, yeah, let's say like that. So 2V1 plus 3V2, it's equal with, so let's say this one will be 2, so that'll be 6, this one will be 1, so that'll be 8. I'll make it a random number. It's equal with 8. and we can say that 4v1 plus 4v2, it's equal with, so that'll be 4, and then that will be 8, that'll be 12, and we have to find the values. Remember, like, we used like v1 will be should be equal with 1 and v2 should be equal with 2. So you may say, like, well, how do you solve this? Well, it's very simple with normal numbers. You can just do literally simultaneous equations, where you multiply this value by 2, you multiply the entire segment by 2, and then you eliminate the v1 and you have v2 left, and then you just do the calculation and get the value for v2. The problem is we do not use normal numbers anymore. We use complex numbers, and trying to find the value of 2 at an angle of 30 degrees plus 3 at an angle of 60 degrees, v1 and v2, and then other v1 at an angle of minus 20 plus v2. Okay, so let's say like v2, this one will be 2 at an angle of minus 40 degrees. And you may already see the problem, like, how do you apply simultaneous equations to something like this, where literally the angle and the numbers make it a lot harder to do so. Like, how can you find a common between those two values to like take it away? So that will make it a lot more complicated. That's why we have to use the matrices, because we can rewrite the formula as this. We can rewrite it as 2, 4, 3, 4, because they are pluses, they're just like normal numbers, which is equal with this column, which will be 8 and 12. We can write it like this, and it's actually a special format to find these values, that you can say like v1 is equal with, and you replace these v1 values with the answers, that will be 8 and 12, and then you get those two numbers as well in here, so that will be 3, 4, you keep those ones the same, and you divide it by this 4, which will be 2, 4 and 3, 4. And you may say, well, how do you calculate this? Well, when you multiply this side, and this side will be a positive, and you multiply this side, and this side will be a negative. Same for this one. This one will be positive, this one will be negative. And the way you do it, it will be that you do 8 times 4, that will be 32, so that will be a positive 32, and the negative side will be minus, that one will be, wait, is it right? So that will be 36. Actually, might be the other way around. This one might be the positive and this one the negative. Anyway, we'll see. Okay, and then you do this one, so that'll be 2 times 4, that'll be an 8, minus 3 times 4 times 3, that'll be 12. Oh no, it's actually right. Okay, and then that will be minus 4 divided by minus 4, and that'll be equal with 1. And look at that, like, it did give us the answer, because we said that v1 it's a 1, and we calculate it with v1 1, it should be 1, and it is 1. So that's how you use matrices to calculate them. And you can apply the same for v2 as well, but instead of putting 8 and 12 on the first row where v1 is, you just put it on the second row where v2 is. So that'll be 8 and 12 at the second one, and the first one will just have the, no, not 3, that's 2 and 4 from the v1s. And the bottom one just stays the same, so we can just say this one will be minus 4. We can calculate this one, that one will be a plus, this one will be a minus, this one will be 24 minus 4 times 8, that will be 32 over minus 4, and then that one is equal to minus 8 over minus 4, and that one will be equal to 2. So look at that, we get the answers by applying this. And you may say, well, okay Alex, but why do you explain all of this? We are doing mesh analysis. Do we really need it? And the answer, unfortunately, is yes. Because when you calculate the matrix for v1, let's say, and I hate that this is the method you do it, you need to do 2 square polar form that, and then like 3 polar form 20, and then like 4 polar form 40, and then 1 polar form minus 20. And you have to apply this instead of the simultaneous equation, because this requires multiplication, which is easy to do in polar form. And then after you multiply them, you just need to take away them, which again require you to change it back to rectangular form. And after you change it to rectangular form and you get the answers, these two numbers, you again need to do it in polar form to do the division, and after you do the division in polar form, you'll get your value. So you need to like do 3 transformations, 3 conversions when you're applying this method. is the only way that I know how to do it for right now. Probably there's a better way to do them, to solve them, instead of using simultaneous equation or matrices. But for right now, using a matrix is the only way to solve them. And I know it. I mean, you don't know yet, but when you do the problems, it's really hard. You may think like, oh, it's easy, you just apply those simple steps, but it's not that easy. And this one, it's only with 2 values. You can have it like with 3 or 4 or as many as you want, because the matrix does have a limit. But believe me, because it's really hard to do it. I was doing it like for my notes, you know, they have the answers and everything, and it took me ages on the calculations, and also it took me a long time. No, also I got it wrong sometimes. For example, I got for one value 2700, I got for another one like 52, and I'm like, okay, this is definitely wrong. I had to like look back at it. I had to like recalculate the top side of it from the division, and then see where I got it wrong, and then I change it to the right answer. I got the right answer at the end. But I mean, like, I don't even know if they'll give me this in exams, because remember, like, I'm in the first year. This was my first year at university, and we never did this stuff. I just learned it from books, you know, because yeah, that's how I learned without a teacher. But anyway, and I'm thinking like, can you even do this into an exam? Can you even like fill up 2 pages of calculations during an exam to like apply mesh analysis? Because actually it will be easier if I show you than I tell you. So I'll pause the video here, but just to understand the basics, we are going to use this matrix method now. We are not going to use the simultaneous equations because they simply don't work on complex numbers. Alright, I'll pause here and I'll see in a second. So, oh, sorry, the camera shaking. Alright, so I'm back. So this will be the first circuit we do with mesh analysis, and I'm sorry to tell you, but this will be also the easiest one that we do. We got 2 voltage sources, 4 at the phase of 0 degrees and 12 at the phase of 0 degrees. And we also got 3 components. We got an inductor with 4 ohms, a resistor with 8 ohms, and a capacitor with 8 ohms, with 2 ohms. Alright, so the very first step, as you know from the previous videos when doing AC, is to simplify the circuit. So we take every component and we call it a Z. So because these are all in parallel, they are not connected with anything, we can just simply write it as Z1. It's equal with the positive value of JXL, which is equal with J 4 ohms. So that will be the first one, Z1. Then Z2 would be equal with R, which is equal with 8 ohms, and then Z3, it's equal to minus the J value because it's a capacitor XC, and that will be equal with minus J 2 ohms. We can also write the voltage sources here. E1 it's equal with 4 volts at an angle of 0 degrees, and then E2 it's equal with 12 volts at an angle of 0 degrees again. Alright, now that we like simplified, we can redraw the circuit, that we get rid of the components so it doesn't look so complicated. We just place them rectangles. So this is the first source, E1 plus minus, then this is the rectangle Z1, then there's the other rectangle Z2, and then there's the third rectangle Z3, and here it's the source, the second voltage source, E2, and both sources are positives here and here, as you see here. Okay, and yeah, that's it. Also, you may want like why there is no formula page or like that I usually do. Well, it's because it's mesh analysis, and we already did that with resistors, and there isn't really any difference between them. They're exactly the same. The only difference is that we use complex numbers now because it's an AC, they are AC sources. But anyway, let's keep going. So yeah, that's like, because there is nothing changes, nothing new to add to it. Alright, so first step, we choose a direction. So I like to choose this direction here for the current to flow in. So then it will go like this. So the current flows this direction, then that will be a positive, this one will be a negative, then this one will be a positive, this one will be a negative. Now for this side, it goes this way, positive, negative, and then it goes this way, positive, negative. Alright, So we mark the polarities as well. So now we can just write, so this one will be I1 and this one will be I2. So now we can just write it as E1. It's positive because it's got minus plus side, minus, and this one it's a negative because it's got a plus minus side. So basically they conflict with each other. This is the reverse of the source, so there'll be a minus I1 because this is for current 1 multiplied by Z1. Next one is for Z2, and current 1 is going through Z2. It's negative again because they are opposite from each other, they are opposite directions. So be I1 multiplied by Z2, and also will be, no wait, oh no, it's the other way around, sorry, because it's the same resistor. Z2 it's I1, and this one says positive, the minus is in here, and then I2 is in the opposite direction of I1, so I1 would be minus I2 because they go to the same resistor, and that's equal to 0. And now let's do for E2. Let's see here. So this one is going actually in the opposite direction. Actually, all three of them are going in the opposite direction, so all of them will be negatives. That'll be minus E2 minus I2 Z3 minus, let's see here, Z2, and this time will be I2 minus I1 equal to 0. Now we can rewrite and rearrange it like this. We can say that I1 Z1 plus Z2 is equal with, no, minus I2 Z2 is equal with E1. If you might wonder, like, well, why is I1 Z, why are these two values, no, why is this value positive now? Well, it's because we moved this onto this side here, it became a negative, a minus value. This one was a minus negative value, this one was a negative value as well, and then we just switch it and make them positive. So yeah, it's simple stuff. Now we can go through I2, it's equal with Z2 plus Z3. Actually I didn't explain it well enough, sorry about that. I shouldn't like assume that you already understand what I'm writing here. Basically, alright, in this one it's equal with minus E2. Basically what I did, I moved E1 to this side here, which makes it a minus E, and then I1, no, and then because it's a minus and all three of them are minuses, I can switch the sign so all of them are positives. So I1 times Z1 would be a positive, and Z2, because it's already a positive, multiplied by I1, it will still be a positive, so it'll be like I1 Z1 plus Z2. That's simplified in a bracket. And the minus I2 multiplied by the positive Z1, no, Z2, that, okay, so like, I'll make it blurry here. I2 multiplied by Z2, because I2 is a negative and Z2 is a positive in that, in that movement, then they become negative, and we apply the same thing for the second one as well. Okay, I won't spend too much time explaining to you how like I rearrange equations, but anyway, so now you can notice that, well, this is very familiar with the previous equations, you know, when it comes to mesh analysis, and usually at this point you do simultaneous equations, but again you just can't do this one here, so we need to rearrange them again. We need to have the same current on the same side. So then therefore I1, what I mean by the same side, like in the same order, you'll see in a second, it's equal with Z1 plus Z2 minus I2 Z2, and then minus I1 multiplied by Z2, and then this will be plus, because it's positive, that will be I2 plus I2 bracket Z2 plus Z3. Alright, so, and then this one will be equal with E1, and this one will be equal with minus E2. Alright, so this is how we rewrite it again, so we get the same currents under each other, so it's a bit less confusing. And now here it's where we apply the matrices. So then we'll try to find it for I1. So I1 will have to replace it with the E values. So then I1 is equal with E1 minus E2, and then here for the second one, which is for the second line, we just keep the I2 values, and that will be Z2 plus Z3, and close this one, and then under is just these two equations really. So that will be Z1 plus Z2, this one will be Z2, this one will be minus Z2, and this one will be Z2 plus Z3. Actually, this one is minus Z2 as well. Sorry about that. This one is minus as well. I almost forgot to put the signs. Okay. So, and then we can also rewrite them because we need to multiply them in a cross area, like across here. We can rewrite them as E1 Z2 plus Z3 minus E2 Z2 over Z1 plus Z2 Z2 plus Z3. If it's not obvious, we multiply them together, minus this one will be Z2 squared, because Z2 with multiplied by Z2 that simply give us Z2 squared. Alright, hopefully you saw what I did there. Okay, we don't have any more space on this page, and I won't write it on the other side because you can see through it and that's annoying. So I'll just simply write it on a new page and we'll keep this one next to us. Alright, so now we can also rewrite it as, we can rearrange it again to make it even, sorry, there you go. We can rearrange it again to make it even a lot simpler, and we can rewrite it as bracket E1 minus E2 Z2 plus E1 Z3 all over Z1 Z2 plus Z1 multiplied by Z3 plus Z2 multiplied by Z3. Alright, now this will be the hard part, which will be the calculation part, but this is still an easy variation of that because there aren't too many phases coming in. So then I1 will be equal with E1, that's 4 volts, you can see it here actually. Let me bet it because there you go. So E1 that's 4 volts, E2 that's minus 12, they are both of them on phase 0. Okay, and then Z2 that is 8 ohms, so that will be multiplied by 8. Okay, plus, alright, and then we have E1, which will be 4 multiplied by Z3, which is Z3, that will be minus J, yeah, minus J2. Alright, and then under Z1 that will be J4 multiplied by 8 plus again J4 multiplied by minus J2 plus 8 multiplied by minus J2. Alright, now let's go to the next step, which is simply calculating them together, and by calculating them together I mean just multiplying them. So then that will be equal with minus 64 minus J8 over J32 minus J28. Is it 28? Yes, I think it is 28 actually. Let me check. So this one will be a negative J, but there has to be J squared. This one will be a positive J. That J will be equal with 4, that will be 32, and then 32 minus 16. That gives me 16. Oh yes, it is. Oh no, sorry, I misunderstood my writing. This one is J4 minus J2, so that will be minus, let me write again, minus J. It meant to be squared 8, sorry about that. I thought it was like 28, and after that I wrote it ugly. Minus J16, this one makes a lot more sense then. Alright, I'll be divided by that, and then that one will be equal with. So another thing that I thing we didn't really use before much, but now it's a good time to bring it up, is that j is actually equal with square root minus 1. That's why it's an imaginary number, because you just simply cannot calculate this. So then j squared will be equal with square root minus 1 squared, and then that one will simply be equal with minus 1. Right? So that's why when you have here j squared minus 8, we just do like minus 1 multiplied by minus 8, because the minus and minus from the previous one makes it a plus, so that'll make it an 8. So to do the calculation for this, so that'll be 64 minus j8 over 8 plus j16. Alright, now we can divide this one because it's a rectangular form, so we need to convert it to polar form. Z is equal with 64 squared plus 8 squared, and that's equal with 64.5. And then the angle is equal with 10 to the minus 1, 8 over 64, and then that one is equal with 7.125. Now we need to do for the next one, which is the one under, so Z is equal with square root 8 squared plus 16 squared, which is equal with 17.89. And then the angle is equal with 10 to minus 1 at 16 over 8. And that one is equal to 63.43 degrees. Alright. And then we can rewrite this one. So therefore, let's see, minus 64. This one will be minus 64.5 at an angle of 7.125. Alright, and then we divide it by 17.89 at an angle of 63.43 degrees. Then that one will be equal with 64.5 at an angle of minus 172.875. All of it divided by 17.89 at an angle of 63.43 degrees. Alright, so now we can write the answer, like we can calculate into the division but in the polar forms. So we can get either 3.61 at an angle of minus 236.3 degrees, or maybe if you want the positive value, we can add it by 360 degrees, and then we get like 3.61 at an angle of 123.7 degrees. Alright, so this is for the first current. Yeah, I know, it's pretty long for only one current. Now we need to calculate for the second current. So then I2 is equal with Z1 plus Z2. Remember, now we replace the side of the I2, because on the first one we replace the side with I1. Now we're with the E1 in E2. Now we use E1 in E2 to replace the side with the I2 while we keep the I1. And don't worry, the bottom value, this value will always be the same. So that one will always be 17.09 at an angle of 63.43. That'll be Z1 plus Z2 minus Z2. And then this one will be E1 minus E2. Right, because these two do like this, and then this one will be Z1 plus Z2 minus Z2 minus Z2, Z2 plus Z3. There we go, we close this one, which will be equal with, so now we multiply this though, so that will be minus, because it's a negative value and the multiplication on this side it's a plus value, that will be minus Z1 plus Z2 E2 multiplied by E2, and then this one is a negative multiplication, but because it's a minus on this side, we can simply write as plus E1 multiplied by Z2. Alright, then we'll all of it divided by 17.89 at an angle of 63.43 degrees. Alright, now we go to the next step, which is to calculate these two values here on the top. So then this will be equal with E1 minus E2 Z2 minus E2 Z1 divided by 17.89 at an angle of 63.43 degrees. That will be equal with 4 minus 12 multiplied by 8 minus 12 times J4, all of it divided by 17.89 at an angle of 63.43 degrees. Then this will be equal with minus 8 times 8 minus J48 over 17.89 at an angle of 63.43 degrees. That will be equal with minus 64 minus J48 over 17.89 at an angle of 63.42. Alright, now we just have to rearrange this on here to make it into polar form. So Z will be equal with square root 64 squared plus 48 squared, that equal with 80, and then the angle is equal with 10 minus 1. Remember, those both values are negatives, so then they will just cancel each other and become a positive, so that will be a positive 48 divided by 64. That's equal with 36.87 degrees. Therefore, we can use either the value of minus 80, remember there's a minus before all of this, minus 80 at an angle of 36.87, which is, which is equal with 80. We added by 180 to make it from a negative value to a positive value. 80 at an angle of 216.87, or we can take away 360 degrees and write it as 80 at an angle of minus 143.13 degrees, depending on your preference and how you want to do it. Alright, so I just a bit tired, and hopefully you saw all of that. Now we will write, actually let's write on the next page, we can't fit all of it here. Don't worry, we are on the last step anyway. So now we do the calculation. That will be 80 at an angle of 216.87 divided by 17.89 at an angle of 63.43, and that's equal with 4.47 at an angle of 153.44, or 4.47 at an angle of minus 206.56. Okay, so that one will be the current I2. Now to recapitulate, we can rewrite it as I2, it's equal with 4.47 at an angle of minus 206.56, or if you add it by 360 degrees, 4.47 at the angle of 153.44. I1, it's equal with 3.61 at an angle of minus 236.3 degrees, or we again add it by 360, so that would be 3.61 at an angle of 123.7 degrees. Alright, so this one was the first one and the simplest one, and you can already see why I don't like matrices, because believe it or not, why is this one the simplest one is because there is no irregular phases. When you look at this one, you can see that all the phases are nice until we convert them, but they are still nice. Imagine when you start with a phase of 20 degrees here and a phase of 30 degrees here, and some random phases for the Z values, because there might be more than one component, maybe like an inductor and capacitor connected together, or inductor and resistor connected together, so the value would be different. There are so many things that you need to consider when doing these problems, but this one is the first one, is the simplest one, and we are going to go to the more complicated ones just in a second. I need to drink water. And these are the solutions. And again, if you try to apply simultaneous equations for these values here, for these two equations, then I'm sorry, but again, you just simply cannot do that, because you need to have it in matrix way, so you can calculate with complex numbers. If you don't do it this matrix way, then you can't really calculate the complex numbers because you never find their common factor. Alright, but anyway, I'll take a break and I'll drink some water and then I'll come back. So just a second. Alright, by the way, these videos might be a lot shorter than usual, and that's because we are already at the last example, which we will do today only 2 examples. We did the first example, which was this, just not a good paper. There goes this one here with a nice drawing, which is a simple one that has only one component of each in parallel, while this one has multiple components and the sources are different. Instead of being on this side and this side at the very end, it will be on this side and this side instead. And you may say like, well, Alex, why are there only 2 examples? Aren't you the guy that says we will do many examples with many types? Well, yes and no. For example, I would also have liked to do a 3-loop one as well to show you how I do it. But let me tell you what the problem would be. This is like, it's not really a good one. It's like, not a good one. This is just like something that I wanted to try. So I made this one and I was thinking, okay, so how can I like calculate the 3 loops going through? And then I realized, well, if I have 3 loops, the big problem is that I'll have 3 currents. I'll have I1, I2, and I3. And the problem of having 3 currents is that I'll have 3 equations. I have the equation for I1, I have equation for I2, and I have equation for I3. And you may think like, well, that's not a big deal, you know, because, you know, you have, let's say like Z1 plus Z2, something like that, you know. You know, you mark it in and you say like, well, that's not so bad. Yeah, but again, remember that even an equation of 2 by 2 is difficult. Imagine doing one 3 by 3, where you have like the Z values here, something like this. Okay, and then we have E2, and then we have like, I don't know, E3 or something like that. And you have like 3 by 3, you know, and then you have something along the lines of these ones. Wait a second, then we have like Z3 here, let's say, and then Z2 plus Z5, whatever. This is random. And imagine like you'll have this and you'll have to calculate this. And you know, like on the 2 by 2 it's simple because like you have the values here, you know, you have like 5, 6, 7, 8. You have this, you just multiply this one by this one. That's simple, and this one is positive, this one is negative. Now on a 3 by 3, the way you do it is you multiply these ones, then you multiply these ones, and you lose back to Z3. So you rewrite like Z1, Z2, Z3, and then we write Z2 plus Z2, Z4 plus Z5, and Z2 plus Z5 again, or something like that, Z4. And then it just reloops, you know. You just need to redo the multiplications again in that direction. And not only that, you need to do it 3 times in this direction, you also need to do it 3 times in the opposite direction as well. So in this direction, which is, actually I mean mark it red so it's more permanent. It's not like I care about the values, which is even worse. So in total, I would have to do 6 calculations where I need to remember that these are the positive ones coming from up to down, and remember that these are the negative ones coming down to up. And not only that, I need to do it 6 of them, but also remember we have the bottom values that we need to calculate as well, that are like a 3 by 3 as well. Let me mark them with X's. So we'll have the bottom one as well to do. So we'll have another 6 ones to calculate. You know? Like this, another 3 ones to calculate. And that will make another 6. And with these 6, we have to calculate 12 equations in total in a way. And do the conversions and everything. And you may say, well, Alex, yeah, but isn't this kind of like what you have to do? And I'm like, sorry, but I just can't bring myself to do so. Because, especially this one here, it was so difficult simply being like this, that I simply just cannot do a 3 loop. Again, remember, I did so many mistakes when I tried to calculate stuff like this, which it's only 2 components. It's a simple 2 by 2 matrix instead of a 3 by 3 matrix. And I still got it wrong sometimes. And I don't know, I think it's because of my calculator. Like, I don't think everybody calculates it manually, like there's the manually the transformation and there's the matrix manually as well. I think they have like special calculators. So this is the calculator that I'm using. It's the Casio. It's like the 85 GTX. The normal one, the classic one that you take it in exams everywhere, where you simply have the tan minus and the cosines and the sines and the powers and the basic stuff. I think I think when people calculate this circuits like this with matrices and stuff like that, I think they have the extra modes that allows them to use matrix on it and allows them to use complex numbers on it as well instead of just the normal numbers. You know, I think that's how they like calculated it. I don't know, maybe I'm wrong, maybe like I'm just too lazy to calculate them. But again, like, well, it took us like 3 pages. Nah, 3 pages is exaggeration. It's more like 2 pages, I'd say. So it took us like 2 pages to calculate the first one. It took us like 2 pages, and it's got only 2 loops. Imagine like having to calculate it for like 3 loops, and it's like we had to do 12 multiplications. We had to do only 4 multiplications in that one too. So yeah, if you're curious, like if I'm going to do in this video this one with 3 loops, the answer is no. I won't, because I simply cannot. I simply don't have the energy to do it, and I know for sure that while doing all of these multiplications to find them, I will eventually do a mistake on it and I'll get it wrong. So it's better to like not do these ones. So I don't want to teach you wrong, and I don't want to teach you something that I can't do. Maybe I will come back when I get like one of those special calculators, or I learn a better way to calculate them instead of like using matrices. But for right now, I'm sorry, but I simply can't. I simply don't know how to do them. Actually, I know how to do them because you just apply this formula again. I just don't know how to calculate them, and doing the calculation so many times. Because again, remember, like not only that we need to do it twice for every unknown value. Now we have 3 unknown values, so we have to do it like 3 times for the unknown values. So that will add another like different metrics 3 times. It's just a mess when trying to do it like 3 loops. So that's why I didn't solve anything for 3 loops. I did start it here, like I was thinking, because usually when I do it, I just draw the random ones. I just draw like this, and then I'm like, okay, fine, what should I put? Like, let's call this one 6, this one 8, this one 20, or something like that. But anyway, so with that explanation out of the way, let's get going with the next one, which will be the last one for today, which will be this one here. This one's again about 2 pages of calculations. My god, I really miss normal numbers, because it was so much easier when there was only resistors and voltage sources or current sources. It was so much easier to calculate something with only those two. And now with inductors, capacitors, and complex numbers, it's just not the same anymore. It's just really hard. At least I'll be prepared for next year. I think I'll be quite ahead of the others next year, because I don't think they'll teach us all of this only 1 week. By the way, I'm just writing the Z values for them while I rabble on, because I don't think they'll teach us this in only 1 week or 2 weeks. Again, unless they show us like a better way to calculate them, because this is actually quite important, and also it's quite hard as well. So I think it will take our lecture about like 2 or 3 weeks or something like that. So if you're still watching with me, like, and learning alongside me, then you should be happy that you'll be like so much more ahead, especially if you're in the first year as well. I hope I'll be ahead. I mean, like, I'm doing these preparations just to like, how is it called, just to be ready for the next year, for the second year. And I don't mind to learn stuff that I'll use in second year as well, as long as it's on my level. Like calculating 3 loops is just beyond me, to be honest. Okay, so just a second. Sorry about that. I keep getting interrupted. Anyway, so yeah, I just like to prepare for the next year, and I guess that's why I start doing this. Actually, I start doing them for myself. They have like kind of like notes for me to listen to. but it doesn't really take me too much to teach as well. But the Z1 it's R1 plus JXL because they're connected in series, and Z2 it's R1 minus JXC. It's a capacitor, so it's got a negative value, and they're connected in series, so you can couple them together. If they are in series, you can like get them together inside the Z value, but if they are in parallel, you can't really put them together with the Z value. Just so you know. Alright, now we have to do the redraw it. So we now see the source, then we draw this one, Z1. We go up this way, down this way, and then this rectangle will be Z2, and then the third rectangle here, this one will be Z3, and then this one will be the second source. So this one will be E1 plus minus, this one will be E2 minus plus, then they will be all connected. There you go. And now we just need to choose all of directions, so we'll choose this direction, I1, and then this one will be I2. We check the polarities, so the current goes in this way, so that'll be positive, that'll be negative, that'll be positive, that'll be negative. This current coming this way, that'll be positive, that'll be negative. Then this one will be positive, this one will be negative. And that's it really. Now we can just write it as a formula. So E will be, so then I1 goes through Z1, so Z1 and to Z2 plus Z2 minus, and then IZ2. This one is basically like the previous one that we did. Let me get the page here. There you go. This one is like this one. It's basically the same principle as this one, but instead of rewriting those two together, I just kind of like skipped to the last step, just write it in the simplified form because it's simply faster, and I think you already know how to do it. Just equal it, and we add those two E's together because they are together inside current one, so that'll be E1 plus E2. Then I2 it's equal to Z2 plus Z3 because it goes through these two resistors, minus I1, this one is I2 as well, so I1 through Z2, and that's equal with negative E2. Alright, now we can rewrite this one like this. We can write it as I1 Z1 plus Z2 minus I2 Z2, it's equal with E1 plus E2, and then this one I1 Z2 plus I2 Z2 plus Z3, it's equal with minus E2. Alright, if you wonder like why do I keep changing like this instead of just leaving them like this, again remember it's very important to have them into the proper order. Like if this one is I1 and this one is I2 and I try to apply matrices on it, it doesn't work. You need to make sure they are multiplied by the same value, okay? Because if it's not, then it will simply not work. Alright, this time let's like makes it a bit, let's start with I2 instead of starting with I1. It doesn't really make a difference because you still apply the same method, but still. So I2 is equal with, and then we use matrix Z1 plus Z2 minus Z2, and E1 plus E2 minus E2. Again, we replaced the I2 side with the results, which is E1 plus E2 and minus E2. With this, so we wrote them here, and Z1, I1 just stay the same here, and then we divided by those two equations. So the matrix of Z1 plus Z2, this one will be Z2, this one will be minus Z2, and this one will be Z2 plus Z3. Is this a minus as well? Yes, it is. Sorry about this. This is a minus as well, so this one is minus as well. Sorry about that. Okay. So now we rewrite it like that, and we can simplify it as we will multiply these two together as a positive, these two as a negative, these two as a positive, these two as a negative. So then that will be minus Z1 plus Z2 multiplied by E2 plus Z2. This is a plus again because minus and minus, they make a plus, so that's just simply be plus E1 plus E2. Alright, and this is a minus because yeah, E2 it's a minus, so plus and minus, that gives you a minus. All divided by Z1 plus Z2 multiplied by Z2 plus Z3 minus Z2 squared. Alright, and then this would be equal with, they're gonna be like put the under Z2 E1 minus Z1 E2 divided by Z1 Z2 plus Z1 Z3 plus Z2 Z3, and that would be equal with 8 minus J16 close the bracket multiplied by 16 at an angle of 20 degrees minus 2 plus J4, and this one will be 10 at an angle of 0 degrees, and then all of it divided by bracket 2 plus J4 close bracket multiplied by 8 minus J16 plus 2 plus J4 multiplied by J12 plus 8 minus J16 multiplied by J12. Alright, it's quite a long equation, but don't I do the calculations. But first we need to like simplify, convert it like the J values. So that would be 82 plus 16 squared, that's 17.89. The angle is equal to 10 to the minus 1, that's 16 over 8, and that one will be equal to minus 63.43. Z is equal with 2 squared plus 4 squared, which is equal to 4.47. Then the angle is equal to 10 to the minus 1, 4 over 2, that's equal to 63.43. This side's a positive because one of the values was a negative. So yeah, no wait, this one, one of these values, this one was the positive, this one is the negative one. Okay, now let's go to the next one. Let me turn the page where I have all the answers because I'm not going to calculate. Imagine like you see it this fast because I already have the answers for the calculations. Imagine if you're me and you had to do every single calculation like individually on the calculator, and just keep writing on it. Man, I don't know, this is not one of my favorite like topics to teach, not to teach, to learn with you. Yeah, let's call this like learning together, to learn with you, because yeah, there are so many things to calculate. It took me so long to like get the right answers. I think they are the right answers, I'm not 100% sure to be honest, but anyway, let's rewrite it as 285. Oh no, I'll write it on the new page, actually it's easier. So then we will rewrite the answers for this big equation in the simplified form. So then we'll get something along the lines of 285, the 0.28 at an angle of minus 43.43 minus 44.7 at an angle of 63.43 degrees, and we divide all of it by bracket 80 plus bracket minus 48 plus J24 plus 192 plus J96. Again, I had to like convert this from polar as well to like get the J values, but then I'm not going to like bother you by writing all the calculations down. At this point, actually at this point, I learned how to do it by heart. Like I know how to convert them for how often I did so. I just need to like write the number down so I don't forget it, and that's it really. But anyway, okay, so that'll be 285.28 minus 43.43 minus 44.7 at an angle of 63.43 degrees. All of it divided by 22 plus J120. Okay, Let's do the conversion, I guess. So x is equal to 85.25 cos minus 43.43. Since this is at the end of it, so that'll be 207.15. Y is equal with 285.25 sine minus 43.43. That's equal with minus 196.1 degrees. Alright, next one is other x, that's equal to 44.7 cos 63.43 degrees, that's equal to 20, and then y is equal to 44.7 sine 63.43, that's equal with 40. Okay, now we need to calculate the z value. So z is equal with 224 squared plus 120 squared, that's equal with 254.12. Then the angle is equal to 10 minus 1, that's 120 over 224, that's equal with 28.18 degrees. So then this answer, I'll write it right here, it will be 207.15 minus J196.1 minus 20 plus J40 all over 354.12 and an angle of 28.18, and that will be equal with, if you do the calculations here, that'll be 187.15 minus J 236.1 divided by 254.12 and an angle of 28.18. Now again we need to do the conversion here again. So you can see like how many conversions you need to do. So 187.15 squared plus 236.1 squared, and that would be equal with 301.3, and then the angle is equal with 10 minus 1 minus 236.1 over 187.15, and that's equal with minus 51.6 degrees. And then 301.3 at an angle of minus 51.6 degrees divided by 354.12 at an angle of 28.18 degrees, that will be equal with 1.19 at an angle of minus 79.78, and that will be I2. Alright, now we have to go to the, now we have in front I2, so that's the answer for I2. Okay, so I mean, look at all of this. All of this, it's only for one number. And again, remember, this is the smallest matrix. It's a 2 by 2 matrix. When you do a 3 by 3 matrix, you need to do, instead of like those simple 4 multiplications, you need to do 12 multiplications. Again, like, I hope you see why I don't want to do like a 3 loop circuit, because it will simply take too long if I do it in my method, where I have to like manually convert it and add it and multiply it. And not only that, but also like there's a chance that I'll like multiply or get the wrong number, and then it messes up everything. Anyway, let's keep going. Now we are on the last one, which will be I1. Because remember, all of this is just only for I2. Now we need to find I1 as well. That'll be E1 plus E2 minus E2 minus Z2 plus Z3. There you go, that's goes in the matrix. Over at the matrix, Z1 plus Z2 minus Z2 minus Z2 plus Z3. We close this one as well, and now we can just write it. Alright, I won't bother with this bottom one because this one stays the same, so let's just rewrite it as E1 plus E2 multiplied by Z2 plus Z3 minus E2 multiplied by Z2, which is equal with E1 Z2 plus E1 Z3 plus E2 plus E2 Z2 plus E2 Z3 minus E2 Z2. If you want like where I got this long number, well, remember they are two, as you call them, how do you call them? Not equations, you call them something else. It's basically two like numbers in a fraction multiplied together. So you do like E1 times Z2, you do E1 times Z3, E2 times Z2, and E2 times Z3. And that's how I got like these four values here if you're curious about it. So basically you just multiply this one by this one, you multiply this one by this one, you multiply this one by this one, and you multiply this one by this one. We have done, I'm sure you've done this in primary school, but I forgot the name of it. But anyway, let's keep going. Oh yeah, and the last one minus E2Z is just this side here. Alright, so now we need to like replace those letters with numbers, of course. 16 at an angle of 20 degrees multiplied by 8 minus J16 plus 16 at an angle of 20 degrees multiplied by J12 plus 20 multiplied by 8 minus J16 plus 20 multiplied by J12 minus 20 multiplied by, let's see, that's like 8 Z, yeah, multiplied by 8. What's Z, Z3? Z2 it's 8 minus 16, okay, multiplied by 8 minus J16. There you go, sorry about that. So yeah, we have to calculate this, and you can see at the problem that some of them are in polar while the others are just rectangular form. So I had to like convert all of that again, but don't worry, I did it by myself. So let me so after we multiplied them, after I converted them and multiplied them, let me get a new page. Now put this on next to us. Okay, so after I multiply and calculate them and convert and everything, we get the numbers 207.52 plus minus 65.64 plus J 180 plus 160 minus J 220 plus J 240 minus 160 minus J 320. Alright, there we have it. Remember, I just, you may say like, well, it's not that difficult. Remember that I calculate everything that was here. Is how long a calculation, and all of them are complex numbers, so I had to make all of them the same factor to be able to do the calculation. Which meaning that because they are multiplications, I had to change all of them in polar form, and because I can't add polar forms together because they have different angles, I had to revert these ones back to rectangular forms that you see right here. So that was like a process that I didn't show you, that I calculated just directly on the calculator and off camera, so that you don't need to like imagine like if I did all the calculations, this video won't be like an hour or an hour and a half. This will simply be like 4 hours or 3 hours. But anyway, so the answer we get like it's 141.88 plus J 420, and because it's the last one, basically this one is basically I1. I'll just simply like calculate it for you. I'll convert it on camera, so that'll be Z is equal with square root 141.88 squared plus 420 squared, which is equal to 443.32, and then the angle it's equal to 10 d minus 1, 420 over 141.88, which is equal with 71.33 degrees, and then 44.32 at an angle of 71.33 degrees divided by 254.12 at an angle of 28.18 degrees, and all of it will be equal with 1.745 at an angle of 43.15 degrees, and that is I1 in polar form, which is basically the number that we use. Alright, so then I1 is equal with 1.745 at an angle of 43.15. I2 is equal with 1.19 at an angle of minus 79.78 degrees. Okay, now what the values are these? Well, let me, is it on this side? No, it's not on this side. I think it's on the previous one. So I2, yeah, okay. So let's see. We can also find the I value, and the I value, where is it? Oh, it's here. Okay, so we found I1, which is this I here, I1. We also find I2, which is this I here. This is I2, because it's coming from this one. It's coming like that. No, wait. I1 is coming this way. This is I2. Now we can also find I3, or simply I, or something like that, which is like when both of them meet here at this area. I mean, if you want to do it, we can do it. I did it anyway. So, no, actually I need to keep this on. I did it anyway here on the notes, so I can show you how to do it. It's actually really simple. We again just convert these two back to their polar form. No, not polar form, rectangular form. So I1, the x value is equal with 1.745 cosine 43.15. That's equal with 1.27. Y is equal with 1.745 sine 43.15, which is equal to 1.19. I2, it's equal with x, that's equal with 1.19 cosine minus 79.78, that's equal to 0.21. And y it's equal with 1.19 sine minus 79.78, and that's equal with minus 1.17. And now we do I1 minus I2. If the polarity is positive, then it follows the direction of I1. If the polarity is negative, then it follows the direction of I2. So that will be equal with 1.27 plus j 1.19 minus 0.21 minus j 1.17. That's equal with 1.06 plus j 2.36. Okay, so it's following the direction of I1. We convert it again. Z is equal to 1.06 squared plus 2.36 squared. That's equal to 2.6. The angle is equal to 10, then minus 1, 2.36 over, let's see, 1.06, and that's equal to 65.81. Alright, so then the I, it's equal to 2.6 at the angle of 65.81. So if it follows the direction of I1, this one here, then it goes this way, and then it just goes downside. So yeah, I3 it's just in the downside direction. Alright, okay, so there's the answer, and that's how you calculate a circuit like this one here. Let me show you a close-up of it, like this one here. It's a bit hard. There you go. Yeah, and remember, like, to do mesh analysis, now you can't use any more simultaneous equation to calculate it. You have to use matrices. Okay, that'll be the end of the video, and I hope you find it useful. And I'm sorry again that there are only 2 exercises, but as I said, I simply don't know how to do it with 3 of them, 3 loops. And also I don't have one of those special calculators that I can calculate complex numbers or matrices on. So I'm sorry about that, but I hope this is enough for you to show you how to do it. And remember, they're exactly the same formulas as normal mesh analysis, but the only difference is that it's got angles. Imagine it's using complex numbers instead of normal numbers. Anyway, thank you for watching, and next time it will be about node analysis. And that one unfortunately still uses matrices. We'll see when we get to that. Alright, bye.